My name is Pax Haymeyer. I'm the Senior Director of Credit-Bearing Programs here at the School of Engineering for the Center for Global and Online Education. And we've been supporting master's students since the 50s. So we weren't global or online at that time, but we've been here for a long time. And it's my pleasure today to be hosting Professors Monroe Kennedy III and Renee Zhao for our talk about AI and the future of robotics, so the AI Frontier. Before we get started, just a few logistics. As I said, we are live streaming it, and we will put a recording of the talk up on YouTube later. There will be some time at the end of this conversation for a few audience questions, if you have any. So if you think of something while we're in the middle of the talk, note it down, and we'll pass the microphone around at the end. I also wanted to note that if you're a School of Engineering alum, there will be a reception directly after this talk at 4:30. You probably saw it being set up right outside Huang. And then finally, as a segue and a lead-in to the talk itself, I wanted to plug the talk that's happening tomorrow at 11 a.m. between Lily Serafin, the chair of the Board of Trustees here at Stanford, as well as Fei-Fei Li, who's a professor of computer science and the co-founding director of HI, the Human-Centered Artificial Intelligence Center here at Stanford. And that talk is Fei-Fei outlining her vision for the future of artificial intelligence. And what it is embodied and spatially aware artificial intelligence. And what's exciting about today is we have two researchers who are doing cutting-edge research here at Stanford that will make that future possible. And so with that, let me introduce them more fully. So Professor Monroe Kennedy III is an assistant professor of mechanical engineering here at Stanford. He has his master's and PhD from the University of Pennsylvania in mechanical engineering, applied mechanics, as well as robotics. He is also the recipient of the NSF Career Grant. Now I'm going to read this. He is the director of the Assistive Robotics and Manipulation Lab. And so the broad research objectives of the ARM lab is to develop technology that improves everyday life by anticipating and acting on the needs of human counterparts. So this encompasses lots of things, but broadly speaking, robotic assistance, intelligent wearables, as well as connected devices. And we'll hear a lot more about the exciting research that's happening in his lab and the future of robotics as he sees it. Also joining us today is Professor Renee Zhao. She has a BS from Xi'an Jiaotong University and an MS and PhD from Brown in Solid Mechanics. Among her numerous honors, she is also the recipient of the Presidential Early Career Award. And the lab that she directs is the Soft Intelligent Materials Laboratory. So her research focuses on developing stimuli-responsive soft composites for multifunctional robotic systems with integrated shape-changing, assembly, navigation, and sensing capabilities. So what that enables are innovations in soft robotics, in the miniaturization of biomedical devices, robotic surgery, origami robots, and many other things. And so we're also very excited to have her join us today and to share the exciting research that she's doing. So if you could all just join me a moment in welcoming them. We're going to start with a broad question, and we're going to show some slides. We have some show and tell here, so there may be a few logistics as we sort that out. But broadly speaking, where I'd like to start is to have both of you paint a broad picture for us. So I think in popular imagination, when we think about robots, we think about humanoid robots, C-3PO from Star Wars or Data from Star Trek. But what's exciting about the research that both of you are doing is the way it can broaden our horizons and how we think about what robots might look like and might be when they're in the home, on us, or even inside us in the future. So what I'd love is to have both of you briefly walk through what your vision for robots might be. What might this world look like with robots, let's say, in 50 years, or choose a time horizon that you think is reasonable. And with that, I'm going to jump over here and pull up Professor Kennedy's slides so that you can have a sense of some of the exciting robots you're working on.
Thank you very much. I guess I'll go ahead and start. I think it's a very interesting question, and the space of robotics moves so quickly, it's hard to give an accurate prediction in the very distant future. But I think a good indicator to use is really asking the question, what are society's needs, and how might robotics provide that type of solution? And I think we have a lot of really important needs for robotics even today. I'll take a few that come right to mind. If you think about the world's aging population, many people have a lot of their cognitive function, but as you get older, it gets harder to move your hands, and you might need someone to come in and help you do things. If you don't want to actually move to a facility, if you'd like to be able to stay in your home, are there enough people to actually come in and do those tasks for you? Or potentially could we have robots that could actually come into your home and do those tiny dexterous tasks that might hurt or become challenging for you to do, therefore giving someone the chance to actually live on their own even longer. If I move to manufacturing, right? If we think about all the tasks of assembly, it's actually impossible for us to make a pen here in the United States. If you think about the cost of labor and how much you can actually sell that pen for, we can't make it here. But if you wanted to onshore the assembly of different things, what does it mean for robots to be able to do those types of tasks? Or agriculture, if you think about harvesting and planting, those conditions are hard for people to work under and have been since forever. What does it mean to have a robot go into those spaces and do those types of things? And to the side of wearable systems, if someone has some sort of amputation or you begin to lose mobility, can a robot actually be a component of you and actually enable some of those motions for you? And so how would it actually extract your intent? If I have a robotic arm, I don't want it to do whatever it wants, I want it to do what I want. But if I have the inability to fully command every single joint and every single motion, then perhaps I need to be able to have a system that can understand what I'm trying to do, take whatever cues I'm able to provide, and then extrapolate how it can best be an assistant and allow me to do something that's fairly complex. So these types of questions is centric to what my lab thinks about. And you'll actually see on this slide us answering this question in many different domains. So in the top right-hand corner, you see us actually, from a first-person perspective, using an augmented reality headset to see a scene and understand how a robot should move to help you perform a task like pouring. In the bottom left-hand corner is our work on dense tact, where we're actually improving the tactile sensing of robots so they can actually do those complex tasks we talked about. On the bottom right-hand side, again, you're seeing an augmented reality first-person view, and my student in the top right sub-corner, where she's actually controlling a virtual prosthesis to perform a manipulation task, where the system is able to track where she's looking, and then with very small cues from EMG, her muscles, she's able to tell it and give it the arm cues on what it should do next. And in the top right-hand corner, we have an autonomous car that actually learned how to drive and avoid obstacles by watching people. I'll go to the next slide here. But one I'll focus on as a key aspect was the motivating example I gave you a moment ago. We want robots in our spaces doing the really complicated tasks. What does it take to really bridge that gap? What are some of the outstanding challenges? And what might we see robots doing in the next decade and years to come? I think that really comes down to utility and usefulness of robots being able to handle dexterous tasks. So in the top left-hand corner, you saw a robot reaching into a bowl of screws and sorting them. This is our work where we can just reach into that bowl, and just from feeling, we can actually determine what we're holding. In the bottom left, you saw us actually picking up a strawberry and doing it many, many times, and we're able to actually characterize how much damage to the fruits we're causing and how the sense of touch, being gentle, is able to allow us to move these fruits so many times without damage. In the bottom right-hand corner, you actually see us doing work where we're actually able to pick up small items off of tables and do those similar types of tasks. So my lab is asking the question, what does it take to make these robotic fingers capable? One part is sensorizing them. The other part is figuring out how we can extract abilities from people to do these complex things. So I'll end actually with this video of this sensor I'm holding in my hand. This is one of our dense tact sensors. We're continuing to make this smaller. This sensor costs a little bit under $40. Most of that's the cost of the camera, but we're continuing to shrink that down. And this is a very important step towards bringing robots into the spaces to do the complex things we need them to do.
That's wonderful. I want to come back to that soon, but I want to give you, Professor Zhao, an opportunity to talk a little bit about your vision for robotics and your research.
Yeah, so my lab at Stanford, first of all, I'm in the same department as Monroe, and we're both in the mechanical engineering department. So mechanical engineering really hosts, well, basically we have a lot of multidisciplinary work going on. In my lab, we specifically work on soft materials, soft composites, and soft robotics. The reason that we're super excited about soft materials and what soft materials can do is that imagine we're talking about robotics to have better interaction with human being. And when we talk about that, especially my lab, we focus on developing miniaturization of soft robotic systems so that we can actually use these systems to guide surgery, like robotic surgery. So that's what I'm going to talk about next. So if we look at the videos that I'm showing here on this slide, we are pretty interested in bio-inspired robotic system, and those systems are based on soft body. So 3 examples I'm showing here. One is earthworm crawling, and second one is the robotic arm based on the inspiration by the octopus arm stretching, bending, folding. So there's a multimodal deformation modes that we can achieve by soft robots. And the third one is based on the elephant trunk motion. So if we look at the common features of these organisms, what we can see is that these are all based on only soft tissue. There's no bone inside. The reason is that compared to the rigid counterpart of a robotic system, where the robots are mainly driven by motors to create degree of freedom. And if we think about something that's soft, because the motion is actually created by the deformation of the soft body. So it means that we have infinite degrees of freedom. So every single material point in the body can deform. So what we're doing here is to utilizing the deformation of the material points in the soft material or soft structure to create multimodal deformation. And that deformation can lead to specific functionalities. So the video that's playing right now, that's based on stimuli responsive materials. So these are the materials that are soft, small, and it's designed under so that they can respond to external stimuli, for example, like temperature responsive materials. And in this case, the temperature can driven the contraction of the polymer material. It's like a muscle contraction, right? So our muscle system is based on contracting, and then we can lift objects. So these are stimuli responsive materials that we design and program so that as a very small system, it can deform everywhere along its soft body to generate bending, twisting, and can lift object and interact with object. And we are utilizing these systems to provide, first of all, as I mentioned, infinite degrees of freedom, and also enhance the movability and also the steerability if we are thinking about utilizing this robotic system to navigate inside of human body. Of course, if we want it to be soft, we don't want a rigid thing, right, to navigate in human body if we're thinking about robotic surgery. And the second video showing here is an origami-based design. So that's a foldable system, and we can use external magnetic field to control the deformation of it and to give us stretching, contraction, and bending and twisting motions. So these are the motions are very important in terms of manipulating objects and also navigating in human body. Later on, I'm going to talk about robotic surgery and how we can by utilizing this stimuli responsive materials. Another key advantage here is that we separate the control unit from the robot itself so that we can actually achieve the miniaturization of the system. So the next slide is actually more exciting. So the first video on the top left, and what you're looking at is a mechanical thrombectomy device. I will start from a question to the audience. How many people in this room has a friend or a family member ever got a stroke before? Oh my God, it's like literally almost everyone. So if you look at the numbers, 1/3 of the whole global deaths are actually caused by the circulatory system diseases. And more than 25% of the global death is caused by clot-related diseases. So recently we published a paper in Nature. It was very recent, 4 months ago, and we developed a very new, fundamentally different mechanism to treat clot, because currently what's out there in the market, the way of treating clot is really not that good, right? Especially for a stroke patient, blocking the blood flow in the brain, that's basically, it's going to cause death of the patient, right? So if we can figure out a better way of removing the clot in a much more effective way, that's actually will be saving a lot of patients' life in a short time. So the working mechanism of this small little thing, we call it millispinner thrombectomy, and there's a QR code. If you want to learn more, you can directly scan that QR code and learn more information about the technology. So essentially what we're doing is by the combination of, well, of course, mechanical design and also combining it with biomechanics of clot. So the clot is made of fiber network constraining or trapping all the red blood cells. That forms a rigid clot. And what we're doing here is by a spinning component, that spinning component, what it does is that it contracts the clot by densifying the fiber network. In the meantime, squeezing out all the red blood cells. And that we can achieve over 95% volume reduction on the clot. And can very easily remove the clot. And that system is actually extremely small. If we can switch to the camera, I brought one device and I was worried about losing it, so we have already there. And I can probably put a reference of my small finger. Because that little thing goes into the blood vessel, right? So that's roughly 1 millimeter size in diameter. And it's coupled with the aspiration catheter, and once we turn on the device, you will see how fast, in a couple of seconds, it will shrink the size of the clot from this big to only 5% of initial volume, and greatly enhance the possibility and the reliability of the mechanical thrombectomy for clot removal. And more recently, and this is also now we're collaborating, so Monroe and I were collaborating on this even the next frontier or the next generation of robotic surgery is if we, actually, can you play the
Yeah, absolutely.
The top right video? 2 videos actually, top right 2 videos. Yeah, so I don't know if people can see there's a tiny magnetically controlled spinner that is navigating in this true to size cerebral artery. That's a vasculature in the brain. So now we can use magnetic field to drive the navigation of the magnetic spinner. And the video, can you click on the second, the very left, right, top right video? Yeah. So this is actually a real blood vessel, and the magnetic spinner is actually navigating in this blood vessel. It swims super fast in the blood vessel. And can we move to the bottom video? So the last video I would like to show here is that utilizing the same spinner thrombectomy mechanism, you see that the small magnetic spinner is digesting the clot, and it's not causing any fracture of the clot or fragmentation of the clot. It simply eats the clot, and it carries the clot, and then it goes all the way. So we're really hoping, and we do believe this is a very promising technology, can just better save patients' life, especially, I can give you everybody an example here. So at Stanford, for the physicians, they're all like a neurointerventional radiologists. We only have 4 people at Stanford who can conduct the surgeries like this. They really need like more than a decade of training, and so that the surgeon can actually perform the technology based on interventional radiology equipment and technology to treat stroke patients like this. But if we now come up with a robotic system, right? So everything is automatically controlled. We have a robotic arm just to provide the magnetic field, so that a small magnetic millispinner can just navigate in the blood vessel and get to the clot, and then treat the clot, and it goes all the way back and then finish everything. So for a lot of rural area where we don't have very skilled doctors, right? Those patients, they cannot be transferred to a hospital that has a facility or doctor to treat stroke. And they will just, very likely those patients will just wait there and die. So we don't want that to happen. We just want to change that fact, and eventually we have this robotic system ready, and with Monroe's help, and we're creating that closed loop system to be coupled with the fluoro guidance, which is the X-ray system for imaging. And then we're very hopeful that they will do, this will be defining the future of robotic surgery. So this is an endovascular robotic surgery that we're trying to make it work.
That's incredibly exciting. I want to come back to the idea of touch, because I know that's very important in bringing robots in the home. But because we're on this topic of robotic surgery, Professor Kennedy, I'd love to hear what you're doing in your lab around robotic surgery, teleoperation, and sort of building on what Professor Zhao was just talking about.
Absolutely. So I think, you know, our work kind of intersects in thinking about, right, how would you want to control these systems to move, and making robots easier to control and operate at the boundaries of their workspace. So while our work covers a very broad area, one of our most recent projects was thinking about, if I have a robotic arm, or you think about like a robotic hand, and I really want to control it to actually mimic the way a human is able to fully, for instance, extend their arms, extend their fingers, right? Generally, we think in terms of the task space. Where do I want my hand to be? If you think of a baseball player throwing their hand up, or a football player going to catch a ball, they don't have to think about how every single joint is moving. They know where the ball is, and they know where they want their hand to go. And so this is still actually, has been in the past, a problem for robotic systems, particularly when you reach these poses that we call singular poses. So if I fully extend my hand, I can't extend anymore, and I can't come back. And so, but for us as humans, it's not a problem, but mathematically for robots, this can be a challenge. There are techniques like using inverse kinematics, saying, here's what I want to do. If I treat my whole arm as a mathematical equation, how can I move? But this can be relatively slow, and you might not get the best solution. So we found a way to actually do this in real time, which makes it easier for people to teach these systems how to move, drive them to a particular way, which is useful for a lot of our work. And then we have an intersection, which is to say, well, if I want this robot arm over this patient, and this robot arm should be able to fully extend itself to wave over the person, it needs to be able to control wherever it needs to be in order to control that millispinner. So that work of solving how to move in and out of these positions that are difficult in our lab essentially propels Renee's work to control these systems so that we can hopefully automate some of these very challenging surgery tasks.
That's interesting. I would love to hear a little bit more. So you're talking about training the robots to do these things. I know when right now when we think about something like artificial intelligence being trained on the internet and text, can you tell us a little bit more about how do you collect data? How do you train robots in these kinds of very complex data-rich environments?
Yeah.
So if you could.
That's a great question. And I think I'll start off by saying, when you hear things about like artificial intelligence, AI, it becomes this sort of abstract cloud to most people. But I'd like to really just make it more boilerplate, right? At the end of the day, these tools are looking for patterns, right? If I give you a particular input, do I get an expected and repeatable output? Or if that output is within a range or distribution, can I tell you what that range or distribution will be? And if I can capture that correctly, then I can use that to make decisions in my model. And we take this very simple concept, I've just explained to you the most essential aspect of AI, and apply it to many, many different domains. From our fingertip, understanding how the image you see inside the finger relates to the forces, to perhaps as a robot makes more complex decisions, how they might do that. But it's very tempting when you have a hammer to treat every problem as a nail. So I think when you can find really strong analytical solutions, you should use them. And the process I just explained to you, where we're able to actually move into these singular poses, this is actually an analytical solution that we developed, which makes it extremely fast and intuitive, but it actually propels other solutions that might leverage it to make decisions in spaces where maybe there's not really a nice analytical representation. Maybe all you have might be data. If I see a surgeon, for instance, performing a surgery and we want them to train the system how to do it, if it's not going to be a closed loop control problem, we need to collect data from doctors, observe how they do it, and we say, whenever you find yourself observing similar things the doctor observed, maybe this is the clot, this is the thing, what choices, what decisions did they make? You should make a decision that's within distribution of what that doctor made in that scenario. And so that's an example when there's not a really nice analytical representation. Maybe you're needing to learn from humans, understanding how humans perceive the world, and then take actions. If we can capture that, perceive what they perceive, and take the actions they would take, we're enabling these systems to replicate, emulate human counterparts.
That's really interesting. So just to summarize it for me, on the one hand, there are these solutions that can be analytically or through a model and just programmed in, and then there are other examples where it's too complicated or not well defined enough, where you're training it based on observation.
Exactly.
Professor Zhao, would you add anything to that as we're thinking about trying to navigate some of these micro robot or milli robots in the body? Yeah.
Certainly. If you could switch to the stroke slide, and just to add on to what Monroe just mentioned about training the robotic system. So these are actually, so the left-hand side and the right-hand side, one is based on tether system, another one is based on robotic system. It's actually giving us a very good example on why robotic surgery will be the future and why combining with AI is important. So first of all, talking about the current mechanical thrombectomy technology, I would just very briefly introduce the procedure. These are all based on catheters and guide wires that are over 1 meter long. So these systems goes from the leg and femoral artery, femoral vein, and it goes all the way to the brain. And a lot of the patients, especially for stroke patients, think about our brain. So I have an image at the center showing the highly tortuous brain vasculature. A lot of patients cannot be treated by mechanical thrombectomy technology because simply the catheters cannot reach the disease site. It's too tortuous in the brain, and if the catheter does not navigate those highly tortuous environment, it doesn't reach the clot and the patient will not get treatment. And now with the robotic system, and then we switch to the magnetic millispinner, there's no tether. We don't worry about the navigation capability. So the navigation capability is not only about how good the catheter is, it's also about how skilled the physician is. Right? So now if we replace everything with robotic control, basically we don't need to train a physician, like spend 10 years to train how they use the catheter to navigate brain vasculature. Now we have that small magnetic spinner that just be controlled by the robotic arm, and that can be trained and coupled with X-ray imaging, and to map 2D images to 3D vasculature that maps the brain vasculature. And with Monroe's help, right, so he can actually design the robotic control to very accurately navigate or steer or control the robotic motion and also the position in the 3D vasculature in the brain, and very easily to reach the clot site. We don't worry about any human error will be causing the access problem or a difficulty to the clot site. Or we can also think about another disease that's common for people have brain diseases, that's brain aneurysm. Right? So if that is not treated, it causes rupture of the brain aneurysm, which is a hemorrhage stroke. So a lot of these things can be done by robotic system, and with the combination of robotic arm control and also imaging. So that the AI part is actually very important here because training the robotic system to navigate a highly tortuous environment, that's also a very challenging task. So the AI coming in is definitely very helpful in terms of looking at a lot of systems and because every patient is different. The brain vasculature is all different, right? So that training data is actually extremely useful to help with a robotic arm to reach the precision and the speed to get to the disease site and apply treatment.
Can you unpack that a little bit just for everyone so we have a clear picture of what we're talking about? So there's one of these robots, and it's being guided by a robotic arm, I assume through magnets. So can you just walk us through what this particular collaboration you're thinking about, if it reaches its fruition, what it might look like, just to make it a little more concrete? Or
sure.
Do you want to start us off?
Yeah, sure. So I think just the best way to do is actually start on this slide. If you look at this picture she has of the brain, you can imagine a clot site that you'd want to address. And just as Renee laid out, if you don't want to actually send a probe all the way up there, if you want to just send that magnet, maybe the magnet is inserted at the entry point, and then those robotic arms would then guide it to that point of action and perform that action for you, and then guide it back out.
And it's connecting just through magnets.
Just through magnets, and then X-ray to perceive where it is inside of the body.
And the robotic arm has been trained, and it's been trained analytically or through data on how to guide that magnet through these systems, which are going to be unique to every human.
Right.
Yeah. This is very exciting, and I want to move away. So we kind of went right into the human body and where robots will be in the human body. I'd like to take a step back and stay with you, Professor Kennedy, for a moment. Something that you've said that really resonates with me is you said the biggest barrier to robots being in the home is a sense of touch, or even more nicely, a sense of human touch. So I'd love that if you could unpack that a little bit, and then Professor Zhao, I'd love to have you build on that.
Yeah. I think if you think about what the future of robots might be, you might imagine the not too distant future. You might be asked if you want to have a personal robot in your home that can do all of these things. Maybe it's about the cost of a car. What would you need it to do in order to justify that cost to you? Right now, there are certain social robots that exist. They can roll around your home. Some of them can do some vacuuming for you. Maybe you own a Roomba. It can connect you with video calls, but it can't really do your laundry yet. It can't. You have the dishwasher, but you have to load the dishwasher, or your kids have to load the dishwasher. This is not really meeting the need yet. So really, when it has the ability to handle your things, to touch your things, then maybe you've reached a particular point. But it's not enough to just touch. You want it to be able to do things in your environment and not break your stuff. You want it to actually fold the laundry and the laundry to actually be handled correctly. And so when you think about that, right, what does it mean for these tasks to be completed at a level that you value in your home? And so to that end, right, humans, right, we have many senses, 5 senses, but when I think about the 2 most relevant to manipulation tasks, is our sight and our sense of touch. There's this really well-motivated video that shows an experiment in the early 2000s where an individual was asked to strike a match. But then they made their finger numb, and they showed the difference between when they tried to strike the match with no numbness versus numbness. And even though the person is still looking at the matchbook, they can see the entire task. It takes them orders of magnitude, 3 to 4 times longer to actually complete that task simply because they could not feel where the matchstick was between their hands. So touch does not necessarily replace vision, but it's an important part of our life, our internal control policy in order to achieve these tasks. So robots need access to that same information, we believe. And if we can endow them with vision and touch like us, and then give them that demonstration, give them that ability, we stand a chance of them being able to perform things like us, and maybe even one day exceeding those tasks. Maybe they can wash your dishes for 20 years and never break a dish, ever. We'll see.
That's exciting. And so, and I know you showed the sensor that you're working on to enable that sense of touch. Professor Zhao, so you're working on materials that are stimuli responsive. So can you elaborate on how you see that? Elaborate on what Professor Kennedy was saying in terms of enabling robots.
Yeah, definitely. I totally agree that the sense of touch is super important for us to actually identify objects and make decisions. Like for just a very simple example, if we use our finger to touch something, right? So the way that we're sensing either how stiff the material is and the surface roughness of the object is actually through the deformation of our fingertip, this tissue that's actually slightly deforming. So that it's actually based on the soft material deformation, and the whole thing that we are interested in our lab and in general this space is that how to develop soft materials and how to correlate their distributed deformation, which is caused by touching, and how to translate that signal to information we actually need into the properties of the object and what the project is and what the functionality is this object and how are we going to do with this object. So the deformation of it and connecting the deformation-induced signals and into functionality. I think that's what the robotics and the touching related robotics is doing in the space, which is critical.
Professor Kennedy, so building on this idea of deformation, sending a signal back, I know your lab has also worked on prosthetics, and I'd be curious what your thoughts are on that. I mean, is there an ability right now, where are we in terms of, you talked about sort of being able to coordinate with that arm, where are we in an arm that might have a sense of touch? Is that total science fiction right now, or is that around the corner?
That's a great question, particularly leaning into that question for like a prosthetic arm. There's a lot of things that kind of go into that. So perception is very important. We've outlined the sense of touch as being important for a robot and perhaps even for people when we're doing these tasks to make decisions. But when you bring up a system like this that has shared autonomy, where maybe this arm has some intelligence and the person's trying to complete a task, if you want to convey the sense of touch to the person, how can you do so effectively is a challenge. So when you actually, if you've ever seen one of those images that shows the density of sensation on the body, the face has ton of sensory, as does the hands and feet, but the rest of the area is far more sparse when it comes to those nerve sensations for the sense of touch. So if I have an arm, for instance, that's supposed to be manipulating its environment, where can I convey that sense of touch on the person in an effective way? And what is the physical mechanism that I would need to actually accurately represent all the modalities of touch that you might experience? If you think about the mechanoreceptors in your fingers, you have 4 of them, and you're able to sense 4 different things. You can sense shape, you can sense forces, so squeezing something, what's pushing in, what's the friction force, sliding your finger up and down, what's rotating. All of those things are useful when you're holding something or manipulating small objects. You can also do vibration, and you can also get temperature. And you're able to do all of these things at a super high resolution. If you were asked to untie a tiny knot, you could feel where every string was between your finger and how much tension was on every thread. That's high resolution. Where can I put that on the body? The back does not have tons of nerves. Maybe you might think about sensorizing the face. One of my students wrote a paper on that recently, thinking about if you put vibrational motors on someone's cheek, for instance, could you convey the sense of touch from the finger to the cheek? Because you have high sensory areas there, but this is really challenging. Where do you put it? And then what's the sensing mechanism that you use to do that? Vibration modes for touch has been this kind of analog, but they're clearly not the same. You can use temperature, you can use electrostatic, and there's been some really cool work where they actually have a device where it inflates with air and it gives you a little grid to kind of push. But again, I gave you 4 modalities for touch. There was the normal force pushing in, 2 sliding frictions, and a rotating torsion. Those are really difficult to capture in a mechanical device and convey in an area that is already very sparse in terms of its density of nerves. Another opportunity is perhaps wearing augmented reality. So you saw a few in my slides, but if you're wearing a headset, maybe I'm showing you something that's an analog to what you feel. You're touching something, and maybe if there's a force profile, I show you an analog of like where your finger is touching, and I show you that force profile. And you as a human, you learn to map what the robot feels to what you see, and maybe that's an opportunity to do that. But this is the challenge. So the question you might ask yourself is, well, do we need to convey that much tactile information? Maybe it's okay to convey less tactile information. Maybe I don't need that higher resolution. And just like I off-boarded some of that manipulation control ability, maybe some of that perception I just have to leave with the robot as well. But it needed to be trained somewhere how to use it. So we gave all of these examples about robots in the home learning to do these tasks. Maybe those sense of touch for doing those complex tasks can be an innate ability of these types of robots. So if you as the human with this prosthetic one day want to untie a knot, the robot knows how to untie a knot. It just needs to know, what do you want to do? And so you go to untie this knot, it feels what it needs to feel, and you have some progress report, but maybe it's handling all of that high density information and control on your behalf.
That's really interesting, and very interesting to think that you might be learning to touch with your hand through your cheek sometime in the future. That's very weird, exciting to think about. Professor Zhao, I would love to maybe take a slightly different tact in coming back to some of your experiments and research on soft materials, and thinking about we've already seen these wonderful examples of using soft materials or millimeter-sized robots to get into the human body. What are some of the other use cases that you see with these stimuli-responsive materials? Where do you see, if we have a human arm, where do you see an elephant trunk arm, and how might that be utilized? What are kind of the special use cases for some of these? And I will say, the one other thing I'd love, if you can, in the answer touch on, are the origami robots. We've seen a lot of videos. I highly recommend going to both their labs. They have a lot more, but some of the coolest are the origami, especially some of the origami ring structures. So I'd love you to just think about, as you're thinking about these stimuli-responsive materials, where do you think they're going to be used? How are they going to be used in robots out in the world?
Certainly. So when we talk about stimuli-responsive materials, these are the things that can, at some point, replace very bulky systems that are made of rigid robotic system components like motors and with all the cables. Stimuli-responsive materials largely are based on the deformation of soft systems or deformable structures like the origami system that you just mentioned. So the deformation of these systems creates motion. So it's no longer relying on the motor creating degrees of freedoms. Now it's basically the material points that we stimulate those material points. It's like you can think about if you have a needle to stimulate your tissue and you will feel that pain. So basically that does the same thing on the soft materials. We stimulate every material point on the soft body, and the deformation leads to locomotion or leads to functionality. And that the use case of these is especially when we have confined environment or environments that it's just we don't want a lot of cables and bulky systems. And also the soft materials, they have a better way of adapting to very complex environment because their body can be passively deforming to conform to a complex environment, especially in human body, right? So human body is most of the time confined environment, and we want the soft material to be, first of all, actively deforming to reach that locomotion, navigation, and a certain functionality. But in the meantime, it can passively deform without breaking itself apart. If we think about a rigid robot, right? So if you force it to deform, eventually it will break and the motor will not work. But now we're separating the driving force. It's basically out from the robot. So the robot itself, it can be just a piece of soft material or some inactive origami structure. And so for example, just the thermal-driven materials or the magnetically driven materials, the driving force is actually outside. The magnetic field can penetrate human body, right? It penetrates. It's a field. It doesn't require very bulky cables and things like that. So that really reduces the volume or the complexity of the system. So you basically only need to design the deformable part, and then the rest of it, in terms of how you want to control the deformation and the functionality of it, it's just manipulating or programming the external magnetic field. So that's just a different way of thinking about robotic systems. So in our vision is that we want to create a soft robotic system that's inspired by a lot of animals in nature where they don't have rigid bones inside, but they're so agile, right? So let's think about octopus. Octopus, their neurons are actually largely, 90% of their neurons, like their brain, are actually in their arms, not actually for us, its brain is here. Our brain cannot move. Our brain is actually rigid, but for octopus, their brain is actually in their arms. They're actually moving. So their brain is actually deforming. You can think of it that way. So if you can integrate something that can think, directly map it to motion, I think that will be a really, really exciting and interesting way of creating robots.
That's very cool. I want to open it up to audience questions, but just maybe one last question for both of you. You talked about the collaboration with the robotic arm guiding the robot through the body. Any other exciting collaborations you can think of or synergies down the road, Professor Zhao?
So what Monroe and I were working together now is actually a very complex system, and depending on Monroe, so we're like hopefully we can really get there. So what we're doing, because thinking about this. The magnetic spinner I just showed. This is just a very simple demonstration, and we did everything on bench, and you can actually see through those transparent flow model. But in reality, of course, our skull is not transparent, our brain is not transparent, and we need to rely on X-ray imaging to actually see the brain vasculature. And just to map that 2D image to a 3D brain vasculature and then control the robotic arm to very accurately navigating that in that very complex 3D roadmap, that's very challenging, right? So one part is the working mechanism on disease treatment, like stroke, treating clot, brain aneurysm. Another thing is the navigation based on vision, which is X-ray, and that map that vision to the command, basically controlling the robotic arm to get to the right place. So that's a closed loop control, actually needs a lot of like multidisciplinary work. So Monroe is actually working on the control side and also coupling with imaging. And our job is to make sure we optimize the spinner design so that it can overcome blood flow, right? So because in the circulatory system, we're not looking at a a system where there's no blood flow. So blood flow, especially pulsatile flow, that creates a lot of challenges in terms of navigating the small robot to the right place. And also the very complex brain vasculature, the fact that it has so many branches, how to have the very agile design or very rational design of the spinner so that under the robotic arm control, it always can swim against flow. It have the capability of swimming against flow and also always navigate to the right branch to get the disease site. So these are all the very important design aspects, and we all need to work on our own part to, and then synergistically work on this closed loop to make it happen.
Anything else? Any other collaborations even beyond this kind of, you're working on the controls and these small robots? Yeah.
I would just say there's lots of opportunity when it comes to thinking about how humans might also be in the loop in the future. I think our work evolves really, really quickly. And a lot of cool things come out of this. So I wouldn't be surprised if soon there's a new surgery application from a lot of Renee's work. And if doctors need to be more involved or you're accelerating that work, what does shared control strategies look like? How could a robot actually accelerate or make the surgeon's job easier? And so I think, you know, our labs are well poised to answer these types of questions in the future. And, you know, we're better than Stanford to ask questions like this.
Thank you very much. Let's end it on that.